different topic than Fritz was talking about. Now we are talking about machine learning and the very, very basics of machine learning. And very briefly about me, so my name is Heli and the last name is Helskuaho. Anybody can pronounce that. Yeah, Helskuaho, that's correct. Yeah, he knows. Even he can pronounce it. He's a Finn, by the way. So that's why I use name Heli from Finland. But this tells much more than the last name. I have graduated from the University of Helsinki, and I have a master's degree in computer science, specialized on databases and information systems, but currently working on my PhD. I'm done with my studies, but the research is still going on. It will take probably 2 years before I get my doctoral. It could be even more, but usually it's 4 years, so let's see. So my research areas are databases, big data, multimodal database, methods and tools for utilizing semi-structured data for decision making, which means that understanding your data better before saving it when it's all kind of different formats, the multimodal database. And I do it at the same university. I also teach there, and so I have a lot of things to do. I've been working on Oracle since 1993. Actually, I've been working with Oracle longer than that. I also worked with Oracle when I was doing my studies at the university. Actually, end of 80s, beginning of 90s. I feel a bit old now. But I don't put it here because I was not paid. It was just studies that I was doing at the time. Anything to do with data and databases, I love it. That's why my research is related to that too, and that's why I talk about machine learning today. CEO for Miracle Finland, ambassador for EOUC, speaker, author. I have written 2 books. The first one is about database designing, and the second one is about SQL and PL/SQL, which I co-authored with 4 other ACE directors. Very fun project. So I'm a member of the ACE program. Here's more information if you are interested about the program. And then finally to the topic, we only have 45 minutes. So what is machine learning? Machine learning is an important part of artificial intelligence. It teaches computers to learn from experience, like we do. We learn from experience. We make mistakes and then we learn new things. But computers, they have only algorithms to learn from. So they are learning from algorithms. They learn from data and they make predictions based on the data. It's about mathematics, it's about statistics, but it's also about people. So machine learning cannot be done without us. So don't be afraid you will be out of job because of machine learning. In this presentation, I will show many places where we are needed. So the computers can't do it alone. So it is a field of study that gives computers the ability to learn without being explicitly programmed. This is something that Mr. Arthur Samuels said in 1959. So everybody thinks machine learning is something brand new thing. 1959. So this is completely old thing. This is nothing special and new. It's a systematic study of algorithms and systems that improve their knowledge or performance with experience. So it's either learning more, getting more knowledge, or making it better performing. But why machine learning now? 1959, and now we are talking about like it's something new and special. Well, because of improved technology, we are finally able to use those great ideas they had years and years ago. The technology is ready for that. And also the storage solutions, the prices are not that high anymore, and so on and so on and so on. So we are more ready for these ideas. But we also have the pressure because our environment has a need for machine learning. Everything must be efficient and fast and can't cost much. So we are saving by using the machines for the work, getting faster and saving money. So we are able to do it, and we are also forced to do it. That's why machine learning is here today. So it's about artificial intelligence, and it's also about big data. Big data is bringing this pressure for us as well, to use machine learning. But what on earth is this big data? So as a name, I think it's horrible, because big data, it sounds like there's a particular size. When your data is this size, you have big data. But if it's this size, it's small data. But it's not about the size. It's about capabilities. So if you are not able to process your data in the way you usually do the traditional way, it might be big data for some reason. So big data could be when you have an email, but you cannot open the attachment for some reason, or you have a photo you can't edit like you usually do. That could be big data, or could not be big data. So big data is about V's, of course the volume, so it might be huge. But it's also about velocity, which means the speed of data. So the data is coming and flowing very, very fast. And that's one of those characteristics of big data. But it's also about variety, which is different formats of data sources, different data models, different kind of data. We have structured, semi-structured, and unstructured data. So all these three V's are some characteristics of big data. But it's also about other V's. For me, the V is very funny because in Finnish language, the V word is the naughty word. So it's so funny always to talk about the V words. My kids keep saying, "Mommy, you shouldn't be saying V words." But I do say. So it's also about veracity, which means the uncertainty of the data. So some data is very reliable, some data is fake news, completely fake news, and something can be even harmful, maybe a virus. So how do you know? You have different data sources. It's not just your operational database, it's different data sources everywhere. How do you know how certain the data is? It's also about viability, which means that we need to validate the hypothesis before taking further actions. And in the process of determining the viability of a variable, we can expand our view to determine other variables. So it's just growing. And also the value. One data is very valuable, another data is not valuable at all. Today this data is very valuable, tomorrow it's nothing. Today this data is not valuable at all, next week it's the most important data we have in our company. So the value can change. It's also about variability, which means that the meaning of the data can change. Like word in the context of a sentence. Word means something, but you put not in front of the word and it means something else. So depending on the context, the data can mean something else. And also about visualization. Visualization is one of the most important V's because big data, well, it is a lot of data. It's a different kind of data, maybe something you don't even know about. Having a visualized picture of the data will explain it much better to you. So visualization in every level is very important in big data. So there are plenty of challenges. More and more data, the volume, different data models, formats, variety, loading in progress, while data exploration is going on, velocity, not all data is reliable, veracity, we do not know what we are looking for, value, viability, variability, and it must also support non-technical users. Like journalists, investors, politicians, we need to have visualization. And all this must be done efficiently and fast. And as much as possible by machines. And that's why we come to machine learning. So, first of all about machine learning, you need to have data. This sounds very silly, but it's serious. You need to have data. Without data, there's no machine learning. So really, we need the data. That's why big data is one of the factors for machine learning to be so popular. We really need to have data. It cannot be performed without data. So part of the data is used to train the model, and part of the data is used to prove the model. So don't use all your data to build the model. You need to have some of the data left for proving that the model really works. These rules and equations are complex. Let's think about image recognition. It's not very easy to, even with your own eyes, it's very hard to say if this is the same person or not. Is this what kind of animal? If there are leaves in front of the animal face, how do you know this is a cat or dog or maybe a horse? So it's not so easy. Also, constantly changing. All these rules are constantly changing, like fraud detection. So you can't have rules that will apply always. The rules are changing, and that's a good place for machine learning. So the nature of the data changes, and the program must adapt. Because today's spam might be tomorrow's spam. Something that is not valuable today might be very valuable tomorrow. Like predicting shopping trends, it's not easy to predict what will happen next year. So what kind of use cases do we have for machine learning? Whatever. The sky is the limit. Machine learning can be used anywhere. And that's why it makes it a little bit complicated, because my machine learning can be very different from your machine learning. So it can be used for spam filters. That's a very typical example, because we can't have anybody in the company adding new kind of spams in our system. If it includes word this and that, it might be spam or maybe not. So we need to have a machine doing that automatically, because there's always new kind of spams coming. So spam filter is a very classical example. Also log filters and alarms, very typical example. Data analytics, image recognition, speech recognition. I am looking forward to the Finnish version of this. It will be exciting. Poor machine. Medical diagnosis. This is my favorite thing. I'm really looking forward to this, because if the computer would know that I will be sick next week, I could cure myself before getting sick, and that would be great. So any kind of predictions about illnesses or very serious sicknesses would be great. So I think this is really, I hope, very good things about medical diagnosis. Robotics, any kind of thing, machine learning can help. But anything with machine learning is approximation. Machine learning is not giving accurate answers. So if I have this prediction about me being ill next week, it's not a fact I will be ill next week. It's just a approximation that I most likely will be sick next week. But it's not a fact. It's just approximation. So anything with machine learning is approximations. Always approximate answers. Some of these answers are better, some even useful, but some are just rubbish. And this is one of the points where we are needed. Because if the machine is saying there's a big correlation between this factor and this factor, I as a human being can say, no way. They have nothing to do with each other, even though the data would say that they are correlating to each other, but I know there's no correlation, so just stop that and find me something else from the data. Because we have knowledge the machine doesn't have. And it's impossible to teach to the machine because we don't even know where the knowledge is. So the machine learning is finding patterns and trends from the data, and then telling us, I found this, do you find it useful? And we decide. The prediction accuracy is one of the meters that is quite often used. The higher the number is, the better the prediction is. The smaller the number is, probably not working. There are several models used. You choose the best, but still it's approximation. No correct answer. So what do I find the most difficult for a beginner to start with machine learning? The terminology, the words. Because there are so many words related to machine learning, and it makes it complex if you don't understand what the words are and how they relate to each other. And that's why I decided to build this presentation. I first built it to myself to be able to do my work, to understand what I should be doing. And then I decided, okay, why not to come and present to everybody else, because it was a big job. So I find the terminology very difficult. Not anymore, because I have my slides. I go and check here if I need to find how they were related to each other, and you will have the slides too. And the thing is that there are those words for the same thing. There are 3 different words, and I'm always wondering, are they different things or are they the same thing? And it's very confusing. And also, how these terms are related to each other. They talk about algorithm and model. Are they related to each other somehow, or are they a separate thing? So I was thinking I will put all this here in the presentation. Let's see if this clears anything to you. The first thing we have in machine learning is a task. And that's actually the most important thing, because task is, what are we trying to do? What's the problem we are trying to solve with machine learning? And this is once again, one of those things that the computer can't do for us. So we are telling the computer, what do we want to have? What is the problem we want you to solve? So we are defining the task. Then we have the algorithm, which is the experience for the computer. It will learn with this algorithm and with the data, and it will solve the learning problem. This produces the model, and the model is the output of machine learning. And our task is addressed by this model. There are very different models. There are predictive models, descriptive models, and prescriptive models. Predictive model is where the model output involves the target variable. It means like a forecast that might happen in the future. Tomorrow it might be sunny, maybe not, but it could be sunny tomorrow based on the information I have. Descriptive model is a model that output does not involve the target variable. It tells what happened. Today it was cloudy. It's a fact. It was cloudy today. So it's not predicting anything for the future. It's just describing the situation. And then is the prescriptive model, which is the most complex one. It's recommending one or more courses of actions and showing the likely outcome of each decision. So I give you 3 possibilities, depending which you choose. This is what will be most likely the result. This is what will be most likely the result, and this is what will be most likely the result. What should we take? So it's a predictive model, actionable data, and a feedback system to track the outcome. So it's a more complex thing than the 2 first ones. So different kind of models, 3 different kind of models. And all these models are based on algorithms that are different types of algorithms. We have classification models, concept learning, tree, rule, linear, distance-based, and probabilistic. Just some categories, how to categorize the models. Then we have features or dimensions, depending who's talking. It's an individual measurable property or characteristics of a phenomenon being observed, says Christoph Bischoff, 2006, in his book. We are deriving features. It can also be called feature engineering or feature extraction. It means that this is one of the most important parts of machine learning. It turns data into information that a machine learning algorithm can use. So it tells the algorithm what is this data. What are the features we are after? We will talk about features later. Then we have 2 methods or technologies, unsupervised learning and supervised learning. We'll talk more about them later. So first let's talk about the task. So the task is very important. Otherwise, it's no point doing anything. It's very important that we define the task well to be able to achieve something with our machine learning. Machine learning is not only a computational subject. It's not only about math and statistics and that kind of things. There's also this kind of human side that is very important. But still, the learning process is about algorithms. We learn by experience and they learn by algorithms and the data. It's not easy to find the algorithm that we will need for our task, and usually it is a try and error process. So you try with one algorithm, you realize it's not good enough, and you try another one, and you see if that works better. And maybe you can get better with it when you do it more, so you know which category to take and which of those algorithms would be the best for your choice, maybe. But in the beginning, this is probably something that takes a little bit of time. The selection of algorithm depends on many things. For instance, what kind of data we have, what's the size, what's the type, what kind of insight do we want to get from the data, and how those insights will be used. So there's different kind of things we need to consider before selecting the algorithm. And it's always a trade-off between many things. So depending what we want to have. Do we want to have very accurate predictions on the new data? Do you want to have a very fast training process for the machine? Does it have to learn very fast? Or it doesn't actually matter? It can learn as slow as possible, it doesn't matter. Do we have unlimited memory, or we have only very little memory? Do we need to have transparency? So is it okay, it's a black box, I just send my data and I get something out? Or do I need to understand what happened in the process? Do I have to understand every detail? Why was this decision made by the computer? Two ends of the decision. And also interpretability. The ability for me to understand the model chosen. Is it important that I understand it? Or is it okay, I don't understand it? And many, many other factors. And the models, they can be very different as well. They can be geometrical models. A couple of examples here. They could be probabilistic models, logical models. They could be grouping models, or they could be grading models. And they could be, there's plenty of different models that these models could be. The feature. A model is only as good as its features. If we have too many features, too few features, the model is not good. Usually we have too many features. And also its interaction between these features. And I added one line here to remind myself to tell you. So one of the things in a process is that we are pre-processing the data before giving it to our algorithms and models. And in the pre-processing, we might be removing noise, we might be doing whatever, but we can also change the data. If it's too detailed data, like the scale is saying 11.1 kilogram, we might change it to 10 kilograms because that's good enough for us, for our estimations or our predictions. So we might even change the data before giving it to the algorithms. So we are controlling the whole process, not the computer really. So we can even change the data before really starting the machine learning. But in short, machine learning is use the right features with right algorithm to build the right model that achieves the right task. That's what machine learning is about in total. As I said in the beginning, there's two types of machine learning, the unsupervised and the supervised. Usually when people explain these, they start with supervised, but I like to start with unsupervised because in the process, quite often I have data I have no idea what it's about. And I need to use unsupervised before I can really use supervised. And that's why I want to start like this, because this is the logical order to be. Somebody else disagrees. Unsupervised learning is finding hidden patterns or intrinsic structures in input data. While a supervised learning is training a model on known input and output data to predict future outputs. Let's see what that means in more words. So in unsupervised learning, we are learning from unlabeled input data. So we have data we have no knowledge about. Plenty of data about something. And we are trying to find hidden patterns or intrinsic structures in that data. Machine learning algorithm finds those natural patterns in data to make better decisions and predictions possible. I cannot find anything from that data. It's a big amount of data I have no understanding about, but the computer can. Then the computer is telling me, I found this kind of correlation between the data. What do we do? And then I have understanding about the data, hopefully. This is something you typically use when you don't have a specific goal yet. You're having data and you want to understand what to do with it. You are not sure what information the data contains. You want to learn some knowledge from the data, or you want to reduce the features of your data as a pre-processing for supervised learning. The most common method for unsupervised learning is clustering. It is used for exploratory data analysis to find hidden patterns or groupings in the data. There's two clustering algorithms, hard and soft. Hard is the one that you can only, when you have a data entry, it can only put in one cluster. While in soft clustering, you have this one data entry, but you can put it in 2 clusters or 3 clusters, in many clusters. So hard only one, soft maybe several places if needed. So hard clustering there's plenty of algorithms. I put some algorithms here in the slides, so when you want to learn more, you can check them. And I also put this when to use here for each of those algorithms to give some kind of idea when this might be a useful algorithm. Like for these two algorithms, they are useful when you know the number of clusters beforehand. So you have to know you're going to have 3 clusters, and then you can use this. This is, by the way, very common. This is some kind of a little bit changed algorithm for the first one. Then this kind of algorithm would work when you don't know in advance how many clusters you have. In the soft clustering, so we can put it in many clusters. I think the most common one would be this one. The number of clusters is known again. So unsupervised learning was about clustering. Supervised learning is about data you already know. It has labels. You know this is first name, this is last name, you already know your data. So it's learning from known labeled data. You are training the model with known input and output data to predict future outcomes of the data. But remember the uncertainty, the approximation. No correct answers. So in short, it means that first we train, we load the data, we pre-process it, remember 11.1 kilogram to 10 kilogram, removing some of the data, whatever we do as a pre-processing of the data. Then we learn, using the method and algorithm, we create a model. And we might do this several times before we find the right model. Then we predict. We use the model we just created with new data to prove that it really works. We have new data, we pre-process it, we use the model we just built, and we get predictions. If we're happy with that, we agree that this was the model we wanted to have, we can implement it to our applications. That's how it works. Simple and easy. So there's 2 methods or techniques for this supervised learning: classification and regression. Classification models are trained to classify data into categories. So typical examples. One email, it can be either genuine or spam for the spam filter. So when email arrives, the machine learning is deciding which one it is, a real email or a spam. A tumor is small, medium size or large. A tumor is cancerous or benign. A person is grade-worthy, let's give him or her a credit card. Definitely not grade-worthy, no credit card. So we're just categorizing things in as many categories as we decided. Applications like medical imaging, speech recognition, credit scoring, this kind of use cases. So typical questions to ask if you're thinking, should classification be the one I should be using? Are, can the data be tagged or categorized? Can it be separated into specific groups or classes? If you say yes, then classification might be the right answer. And also, how many classes you will have, it can be binary or it could be multi-class classification. Also, again, some algorithms for classification. This is probably the most typical one, and here's when to use it. I don't go into details with the algorithms. This is something that when you go further, you might be interested in. This is naive Bayesian. Naive comes with the fact that it's expecting all the features I have nothing to do with each other. That's why it's naive, because of course they have something to do with others. Another example, neural networks are quite interesting, by the way. All kind of decision trees. Logistic regression is, by the way, also classification, even though the word regression. So the regression, so this previous one was about classification, and the other type is regression. So regression is to predict continuous responses. Now we were just classifying, now we are trying to find continuous responses. Like changes in temperature, the temperatures are continuing. Fluctuations in electricity demand, how will it affect to the electricity demand? What kind of predictions do we have that? Applications like forecasting stock prices, handwriting recognition, acoustic signal processing, failure predictions in hardware, electricity load forecasting, this kind of thing. I think forecasting is something that probably brings the right idea to mind. So, two different things, classification, regression. A lot of algorithms for regression as well. Linear, non-linear, generalized linear model, Gaussian process regression model, regression trees. So, however we ended up to what we have a model built, we implement it to our application. But it's never perfect. We always need to improve it a little bit for some reason. We might want to increase the accuracy. It's not accurate enough for us. We need to do something to get it more accurate. We need to increase the ability to recognize data from noise, because we realize the data we get has a lot of noise. So how do we get the noise out from the data? We might need to increase the performance. It's not performing well enough. Or we need to improve one particular measure that is very important to us. And how do we improve the model so that measure will look better? And that's about improving models. This model improvement involves feature engineering and hyperparameter tuning. Feature engineering has two techniques, feature selection and feature transformation or feature extraction. So feature selection is also called variable selection or attribute selection. And that's the problem. You remember features, dimensions, variables, attributes. It's quite confusing. So we are identifying the most relevant features that provide the best predictive model for the data. That's the idea we are trying to get here. What are those features we definitely must use, but there are no extras? We are either adding or removing variables to improve the model performance. There are techniques for that: stepwise regression, sequential feature selection, regularization, and neighborhood component analysis. Then, I don't go to details on this, but I put all the words here so you can Google if you want to learn more about these techniques. Feature transformation is a form of dimensionality reduction. So we are reducing the dimensionality. It's used when we want to reduce the dimensions of the features of the data as a pre-processing for supervised learning, or the data set gets bigger and we can't handle all those dimensions anymore. We need to get the dimensions smaller to be able to handle the data. Examples for that. The feature transformation has three techniques: principal component analysis, factor analysis, and non-negative matrix factorization. Principal component analysis converts a set of observations of possibly correlated variables into a smaller set of values of linearly uncorrelated variables, which are called principal components. So finding the principal components. The first principal component will capture the most variance, followed by the second, a little less, and so on. Factor analysis identifies underlying correlation between variables in a dataset to provide a representation in terms of a smaller number of unobserved variables, the factors. Whereas non-negative matrix factorization, by the way also called non-negative matrix approximation, is used when model elements must represent non-negative quantities, such as physical quantities, like a weight of a person, which cannot be negative. So values are non-negative. Then the hyperparameter tuning. So a hyperparameter, they are parameters whose values are set prior to the commencement of a learning process. The value of these other parameters is derived during the training, but these are set before we start. And hyperparameters control how a machine learning algorithm fits the model to the data. It's an iterative process, as you can imagine. As all the tuning, it's iterative. And there are some algorithms like grid searches or random searches used for that. But a simple algorithm with well-tuned parameters is often much better than a very complex. So like anything else in life, and especially in computer science, the simpler, the better. And that's why we have these techniques to reduce the complexity. But how do I know when to tune? Well, it depends. How does the model perform on the data? Which of the models is the best? Which of the learning algorithms give the best model for the data? And so on and so on. But to be able to answer the questions, we need to have measures. We can measure several things. We can measure numbers of positives, we can measure class ratio, accuracy, coverage curve, whatever, but it all depends what you need to measure, what is important in your machine learning goal. It is experimental objective. Depending in your case what is important, you measure those factors. So how to measure, how to understand what the measures show, it all depends what we are measuring. I have one example here. Usually the accuracy is very important. There's one tool for accuracy measuring. It's called cross-validation. It's also called rotation estimation. So we have the data here, and we divide it, let's say, to 10 pieces, equal pieces. We take the first 9 to train our model, and we use the last 10 for proving that the model works. Then we move forward. We use these 9 to learn the model, teach the model, and we use this to prove that the model works. Then we move again. We use these to teach, and we use these to prove that it works. We use these to teach, and this to prove that it learns, and so on and so on. So we just rotate the whole circle. We do it, if we have 10 pieces, we do it 10 times. Every time we move it one step forward. 9 pieces for teaching, 1 piece for proving. So every piece is used 10 times. So this is what cross-validation is about. And it gives better accuracy. So what should I learn next? There's so much about machine learning. So it's not just, I can't do it because I don't do math. You don't have to do math because there's so many things that you could be doing in machine learning. And machine learning is not just machine learning. There's a lot of new words here. There's reinforcement learning, preference learning, multitask learning, online machine learning, active learning, deep learning, adaptive intelligence learning, and so on and so on. So all these, I put these keywords here if you want to Google more about these topics. And there's plenty others as well. So machine learning can mean very different things to different people, depending what they are trying to do with machine learning. But data mining is something that is used in machine learning. And that's a very typical use case in many of the companies. They are using data mining, which is also a very old thing, not a new thing at all. If you're interested about doing data mining kind of things for machine learning, use SQL Developer. SQL Developer has this add-on called Data Miner. You can just install it there and start using it. I put some articles here. This is how to install it, and there's one tutorial to get started with it. This is a very good way of starting if you don't know anything about machine learning and you want to understand how the process works, because this is how it looks like. You can drag and drop things here. You can use your own data you understand, and you can just see what happens with my data. If I use this kind of model, what happens? If I use that, what happens? If I use this model with this algorithm, then what happens? So this is maybe a good start for somebody who's already using SQL Developer and is interested about data mining. In our book, chapter 10 talks about this, and Brendan also wrote another book about data miner. So if you find it very interesting, these are 2 sources you can find more information. If that's not your case, you prefer using R, and you already have a license for Oracle Advanced Analytics option, R might be your choice. R is in a database, and you can just use that to learn from your data. Chapter 11 in our book, or Brendan wrote another book about R, and there's plenty about R everywhere. It's very popular. Or if you just want to use your SQL and PL SQL, which is your favorite thing. How about predictive queries in Oracle 12? That's also an option. Chapter 12 is talking about predictive queries. And if you don't want to use any of these, you are definitely a Python user, you don't do anything except Java, no problem. Any of these languages has machine learning algorithm libraries. So you can just find the libraries from your language and try that. But start with a data you already know, because then you know what to expect. But any of these will work, no problem at all. And I put here an article, actually, the survey about popularity of different languages. If you want to know what would be the most popular language at the moment, you could go and check and learn that language if you want to start learning new languages. But whatever you do, know that artificial intelligence and machine learning is here today. And it's also the future. So I really encourage everybody to learn more about it, because it is something that is definitely worth learning, and it will be there next year as well. So this is definitely something we should all know at least a little about, and know at least some parts of it. As you already saw, it's a big thing, a lot of different skills needed, but find your place in the machine learning thing. So many interesting areas to learn, so this is really exciting. So just pick your area and start learning. So the time for machine learning is now. Definitely now. We are technically able to use machine learning, and we have the pressure from everywhere to do it. All the V's are giving us pressure to do something with the data that is coming. There are so many use cases for machine learning, it's everywhere. It's about approximation. That's something we need to remember, because we are used to have relational database, which is very fat, right? But this is not so fat, this is approximation. Remember unsupervised learning and supervised learning, the two ways of learning. And the predictive models, classification and regression. Improving the models is important. When we set them up, we need to improve them with either feature engineering or hyperparameter tuning. What to measure, how to interpret whatever we got with the measures is very important. Otherwise, we don't know what to improve and how to improve. And there's so much more to learn in machine learning. Any questions? Happy to answer. I still have 3 minutes. And if any questions, here's my email, here's my Twitter, here's my blog. So far, I mainly blog about data modeler, but the university is pressing very hard. They said you should be blogging also about all the cool things we are doing at the university. So let's see. When I have the time, I probably blog about those things as well. But any questions? I will be here the whole day anyway. Yes?
What are the trends today? Are machine learning moving into OLTP, or is it staying special to projects in data warehousing and so forth?
So the question was, is it only data warehousing and that kind of systems that machine learning is good for, or is it also for OLTP systems? I would say it's anywhere. I might want to learn, so I have my OLTP, which I know so well, but there might be some knowledge I'm not aware of, because it's already a big database. It's been there for 30 years, and I don't know everything in my data. So I might want to use machine learning to understand my data better, even in my OLTP. Like I said, the sky is the limit. With machine learning, you can do anything, even with your OLTP. Yeah. Thank you so much.
Okay.